we're going to look at section 2.8. So this is related rates. I think some of you are going to find this section kind of fun because we start getting into some applications. So on this first page here, we're going to look at functions that involve variables that are changing with respect to time. So for example, on this first one, y is equal to 2x, we are not differentiating with respect to x. So if we're differentiating with respect to another variable, then we have the dy, like on the first one, we do the derivative of y, we're going to have dy dt. And then on the other side, on the right side, we have the 2x. So you're going to have 2, so the constant multiple rule, you have the 2 there. And then instead of that x going away, because it's not dx dx, it's dx dt, we have to show that also. Okay, well, if you think about it, you can see that like in the original function, if the x value is always twice the value, if the y value is always twice the value of the x, then it follows that the rate of change of y with respect to time is going to be twice the rate of change of x with respect to time. All right, let's take a look at this next one. So if we have the equation where the variables are related by y is equal to x squared plus 3, and we're going to differentiate with respect to t again. So when we do the derivative, we're going to get dy dt is equal to 2x dx dt, and then the derivative of 3 is 0, so that's going to cancel out. And then I have this, when x is 1, the rate and change of x with respect to time is 2, and we want to find dy dt then when that x is 1. So dy dt will equal 2, replace the x with 1, replace the dx dt with 2, and we get 4. All right, so that's kind of an example of what it looks like. So sometimes you're going to have to create your own model, or you're going to have to come up with your own equation. So here's an example of one of those. We have a pebble is dropped into a calm pool of water, causing ripples in the form of concentric circles. So if we draw that out, so we throw in the pebble, and then we start getting these concentric circles. So you can imagine what that looks like. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water? So let's say my concentric circles here represent the disturbed water, so it hasn't reached any farther than that. So we're relating the area to the radius. So the formula that we have to use then is simply the formula for the area of a circle. So we'll write down area is equal to pi r squared. All right, and from the information here, we are given the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So they are telling us then the dr dt is equal to 1 foot per second. And it says when the radius is 4, so when the radius is 4, we want to find what is the rate that the total area is changing. Okay, so we're looking for the change in the area with respect to time. So that's what we're looking for. So we take our equation then and we differentiate with respect to time. So we'd have dA dt is equal to, remember pi is a constant, So we can take the exponent 2, multiply it by pi, so 2 pi. R is to 1 less power, and then we need dr dt, because it's not canceling out. We're differentiating with respect to another variable. So we got to find this. So we have the 2 pi when the radius is 4, and the radius is changing at a rate of 1 foot per second. So we get then the rate of change in the area is equal to 8 pi, and area is changing then at feet squared. Well, I don't want to put it there per second. Okay. All right, let's take a look at this. So here are some guidelines for solving these kind of problems. First of all, identify everything that you need, everything that's given. So if they say the rate and change of the area, it's like, okay, so I know that. I know what the area is, or different things. So write everything down. Write an equation that relates the variables, and use the chain rule to then differentiate both sides with respect to time, and then substitute in and solve. Okay, so those are your steps, so you can always refer back to those. A couple of things to remember them, so some hints that might help you, is don't substitute in your values until after you differentiate, so that's important. So do not substitute until after you set up your equation and you actually differentiate them with respect to time. And then another hint, like to get your equations, is look at reference tables and stuff, and take a look at your little calendar. It has, if you have one of those calendars from the school, it has all kinds of formulas in there, so that's a nice place to look to for some of these equations. Take a look at this table. So if the verbal statement is the velocity of a car is traveling at 75 miles per hour, and your x is the distance traveled, then the change in distance, dx dt, is your velocity. So that rate of change then is equal to 75 when the time is 1 hour. If a bathtub is filling at 0.8 cubic feet per minute, and the volume, the V represents the volume of the water in the tub, then dV dt is the rate at which it is changing. So that will equal your 0.8 cubic feet per minute. If you have bacteria is growing at a rate of 15 grams per day, and let's say X is the population of the bacteria, then when you do the derivative, your dx dt then stands for the change in the population. So the dx dt would equal the 15 grams per day. If profit is increasing at a rate of $2,000 per month, and P represents the profit, then when you do the derivative with respect to time, dp dt then is equal to your 2,000. We're looking at how the profit is increasing. So it's the derivative of the profit. So keep some of those examples in mind. Okay, let's try another problem here. Air is being pumped into a spherical balloon at the rate of 4.5 cubic inches per minute. So a balloon, so that's three-dimensional, and so that is changing, it's growing. So that's not just area, that is volume. Find the rate of change of the radius when the radius is 2. Okay, so we need the formula for the volume of a circle. And the formula for that, you start off by writing that down. So what I say, the volume of a circle, the volume of a sphere. So volume is 4/3 pi r cubed. When I look at this, it says it's being pumped into the balloon at this rate. So the 4.5 cubic inches per minute stands for the derivative of the volume, or the change in the volume with respect to time. 4.5 cubic inches per minute. We're given, or it says find the rate of change of the radius, so we're looking for dr dt, that we do not know, when the radius is 2 inches. Okay, so that's what we're looking for. So we're going to go back to our formula, and now we're going to differentiate both sides with respect to time. So dv dt, 4/3 and pi are both the constants, so we can move that out to the front. Now we're going to do the derivative of r to the third, so we bring the 3 out to the front. R is to 1 less power, and then because we're differentiating with respect to time, we also need a dr dt. So when I simplify this a little bit, the 3 and the 4/3 will cancel out the 3. So it looks like we have 4 pi r squared dr dt is equal to dv dt. We're looking for the rate of change in the radius. So this is what we're looking for. So that means we have to substitute in for the other variables. So the change in the volume, we said earlier, was 4.5. So that goes over here. They also told us the radius was 2. So it's 2 squared. And then times dr dt. So if we simplify that, 2 squared is 4. 4 times 4 pi is 16 pi times dr dt. And we get 4.5. So to find the rate of change of the radius, we take 4.5 and divide it by 16 pi. Now let's go ahead and change that to a decimal. So when you divide it out, you get approximately 0.09, and that's the rate of change of the radius. And we said when the radius was 2 and the change in the volume was 4.5 cubic inches, so that is 0.09 inches per minute then. Alright, let's see what the next problem looks like. Okay, a company's profit from selling X units of a product can be modeled by this. So here they give us the equation, so we don't have to go search for one. The sales are increasing at 10 units per day. Find the rate of change in profit when 500 units have been sold. Okay, well at least we have our formula, so let's go ahead and bring that formula down here. Profit, whoops, where did I get that parenthesis? Profit is equal to 500x minus 1/4 x squared. Alright, and then let's see if we can identify sales are increasing at 10 units per day. So the sales are the x. How many of them you're doing? So the dx dt, the change in the sales, is 10. And they say find the rate of change in profit, so we're looking for dr dt when 500 units have been sold. So that means then the x is 500. Alright, so let's go back over to our equation. Let's differentiate both sides with respect to t. So we have dp dt 500x, so we do 500 times the derivative of x with respect to t. And then 1/4 times 2 is 2/4, so 1/2 x to 1 less power times, once again, the derivative of x with respect to t. So here I have 2 dx dt's over on the right side, so let's go ahead and factor that out. So I get 500 minus 1/2 x. So remember, we're looking for the change in the profit. So this is what we're looking for. The change in the sales was 10. So we can put a 10 here. When we were actually, when the rate of change in profit, when 500 units are sold, so the x is 500. So minus 1/2 times 500. Half of 500 is 250. 500 minus 250 is 250 times 10 is 2,500. So that would represent the change in our profit. Okay, and the time was per day, so we're increasing our profit at $2,500 per day. All right, very good, you guys. Whoops, let's go to this one. So now I would like you guys to go to your books, and actually these exercises, you don't have to come up with your own equations, so the equations are there. So you're going to play around with this, and then when we're together in class, then we'll try and do some of the problems where you have to go find formulas or something. So let's just have you work on those. So remember, it's not in the first part, so it's not on the problems that are review problems or the ones that sometimes we do for warm-ups. It's in the actual exercises. So do those first 4, and then we'll work on some harder ones in class. All right. Good luck with those.